I believe that part one got interrupted in the middle of my explanation. So basically 0.88 for MSST, 0.93 for DET. Evidently, DET has a higher factor of safety than MSST. And like I said, DET is less conservative than MSST. So it makes sense that the factor of safety that you calculate in the distortion energy theory will be higher than the factor of safety that you achieve in MSST. Because if I mentioned earlier, MSST assumes that the shear yield strength is 0.5 SY, and DET assumes that the shear yield strength is 0.58 SY. So as you can see, distortion energy theory predicts a higher strength in shear than MSST does. So as a result of this, we have, and again, this is 1 over square root 3, and that comes out of this equation when you set sigma 1 equal to negative sigma 2. So it kind of shows up, you can get a derivation in the textbook, but this is kind of where 0.58 comes from. And therefore, we can make the claim that N DET, the factor of safety in the distortion energy theory, is always greater than or equal to NMSST. And the reason I say equal to is in the case of uniaxial stress. So NDET is equal to NMSST when you have uniaxial stress. So that means you have a stress element that has absolutely no shear and just a bending moment, for example. So what would the Mohr circle look like in that case? It would look something like this, where you have sigma 1, your sigma 2 would be at 0, and then this is your tau max. So if I were to write out the equation for NDET, I would get SY over, and setting sigma, okay, let me just write the equation out. Sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square. And if I set, in this case, sigma 2 equal to 0, because it crosses the origin, this is 0, this is 0, I end up with SY over sigma 1. And there's a square root here. And sigma 1 is nothing but 2 times the radius, which is equal to 2 tau max. Right? And this is, so we have SY over 2 tau max, and that is MSST. So it's possible that they're both equal, and that only happens when you have uniaxial stress. And I wanted to bring your attention to this failure envelope right here. So what happens here is you'll notice that there is an ellipse which models the failure envelope for the distortion energy theory, and then there is an octagon, hexagon rather, that models the shear stress theory, or the failure envelope with respect to the shear stress theory. Now, for example, you've done the analysis, you've figured out your principal stresses, and you realize that you have a value that sits somewhere here. Again, this is plotted as sigma 1 versus sigma 2. Using MSST, it predicts that it will fail. It's outside the failure envelope. But according to the distortion energy theory, it's actually inside the failure envelope and it won't fail. If your stress was here, it would fail in both theories. If your stress state was here, it would pass in both theories, or it wouldn't fail in both theories. So this is important to note, that you'll have conditions where one would say it will fail and one would say it wouldn't fail, simply because one is more conservative than the other. And you'll note that they intersect at various points, right? And this happens when one of the principal stresses is set to 0. So your Mohr circle would look something like this, or it would look something like this. And when that happens, you're basically dividing the shear strength or the tensile shear strength by the principal stress, the single non-zero principal stress, or in other words, the radius of the circle, which is tau max. So this is the static feeder theories we have discussed. There is also one called the normal stress theory. It is a lot less conservative, especially when you're applying shear loads, and it just basically says that N is equal to Sy over sigma, or you mean your sigma 1 or your sigma 2. It's just just sigma 1 or sigma 2. And this is something that we tend to stay away from simply because it doesn't take into account the shear or the fact that a lot of specimens fail at that 45-degree angle. So this is something we will not use. And again, normal stress theory is usually used for brittle materials.